So the first thing I'm going to show you guys is really simply how to create the very basic heat map. So what I have on this map here is, first off, a places point data set. All this is basically is just a city map. If you open the attribute table, it's just a bunch of cities, and they have a population associated with it. I'm giving you this point data set right now, but I will show you how to find point data sets and bring that into GIS for another part of this. But first, I'll just show you basically how to do this. The first thing I want you guys to do actually is, if you look at the map of the United States, it looks weird, it looks flat. We're going to change the coordinate system of this to make it accurate. So I'm double click on there. I'm just going to search for USA in the search bar here. And I'm going to go to the projected coordinate system, and I'm going to go to continental, North America. And generally speaking, when you're working within the United States, I recommend this one, NAD 1983 contiguous USA Albers. When you're just doing a very basic map of the United States, this is actually the best one. So I'm going to double click on this one. Okay. You see, what it does is it makes a very accurate representation of the United States and actually adds in the curvature of the Earth as well. So this is the best coordinate system, bless you, for the United States. Bless you.
What was the system called again?
It's called NAD 1983 contiguous USA Albers. This makes the most sense if you are representing the entirety of the United States, right? If you only want to represent like a certain portion, I recommend looking into the state plane example, the state plane of that city. So what we're going to do is we're going to do a simple population density map right here. So the tool that you want to use is in Spatial Analyst and in Density, and this tool called Kernel Density. There's also line density and point density. I find that Kernel Density actually works the best out of all these. So I'm going to double click on that. It's going to ask you to bring in that point information. So bring in that point places field. The second line of this is going to be what is the magnitude of each point. And basically what we want to do is it's basically going to add a value to each of those points so that areas with higher population are heavier and have a greater weight than areas with lower population. So this field has to be the actual population number. So this actually has the population for the 2000 census, which is outdated. So you're going to have to try to find, if you want to do this kind of thing, find the most recent population numbers. But just for this tutorial, we'll just use that number for now.
Where's the Kernel Density under again?
It is in Arc Toolbox, Spatial Analyst, Density, Kernel Density. And again, if you don't know where anything's located, just go to search and just search for it. Search is that little button up here in the corner, or in the tab. So let's go to Kernel Density, bring in that point data sets, set the population field as pop 2000. I'm just going to leave the output raster as is for now. I'm not going to change this. And then there's two things you need to put in here. First is the output cell size. Sometimes this process doesn't always give you the result you want, so there is some trial and error involved when you're doing this. So generally speaking, I leave these lines as is. I don't touch them all first, and I see what result I get just from the default settings. But one thing I do recommend doing is always going to the environments button and setting the processing extent to same as display, so that only calculates the density for the area within the data frame here.
Do that one more time.
Go to environments, processing extent, and then set this to same as display. So click OK and OK, and let it do its thing. Okay, so when it's done, what you get, now what you see here is something, again, it doesn't look quite right because you always have to do a little bit of trial and error, but let's just see what we get. I think what the problem what we're seeing right now is just that the breaks of classes that's happening on the side here is not distributed in a logical way. There might be some outliers. So if I double click on this and go to the Symbology tab, you want to go to the classified option here, right? If I click on classify, you see that the distribution of the breaks is even, right? Even between each even for each break value. What's probably happening right now is that a lot of the values are within just this first break here, and everything else, there's nothing. So if you remember from a couple classes ago, you want to choose something like quantile or geometric interval. And if you let's say just choose quantile, click OK, and apply, you get a different result. So I would encourage you guys to play around with this classification option here. So let's say let's choose geometric interval and see what we get from that. And you get a different map from that. Let's just pick a more interesting color ramp. Let's say this rainbow gradient here. And you can kind of see now we have a representation of the populated areas, and it makes sense, right? There's the northeast area here, there's the west coast area here, and St. Louis is right over there. So this looks okay, right? But maybe you're saying to yourself, I don't want this level of specificity to my map. I might want a bit more of a generic population boundary, right, to kind of understand where are the major mega regions of the world. And so let's go back to the kernel density and change a few numbers. So go to Arc Toolbox, kernel density, bring in that places point data set, set this to pop 2000. I'm actually going to do this. I'm going to, if you remember what the previous one looked like, it was actually kind of pixely. You can't see, you can actually see the pixels. That's the cell size right here. So just let's make this a little bit smaller. Let's make this like right now it's 0.2. Let's make it 0.15, just to make it a little bit more of a finer gradient. And for the search radius, you're gonna have to play around with this number. I'm not exactly sure, what's the best value here. You gotta try it. Like I think I might have tried a bunch of different options for this area when I was preparing for this class. So, but let's just put in 2, and it might be it's going to be 2 square map units. Again, it's mostly just trial and error. But I'm going to set the processing extent to same as display. And if we click OK, let's see what we get. So this is the result. And you see that it's already looking a lot more blobby than the previous one. This is what I was going for. It's a lot more generic. It's a lot more of a wider density map. So you might decide to mess with those kernel density values if you're going for something a bit more generic as opposed to something so specific like this. But let's change the symbology for this again. So let's go to the classification, set this as, say, geometric interval, click OK, click apply. And you're going to see, like, actually there is an interesting pattern what's going on here. Let's maybe make this another color gradient, like here, for instance. And so this is an interesting representation of the population density areas in America. And one thing you can do is you can take these rasters, right? It's basically a contour drawing, so you can actually take contours from this. So we're going to take this new raster and we're going to plug it through the contour function, which you can find in 3D Analyst, raster surface, contour. So we're going to drag in that option, that new raster in there. If you remember when I did the contour tutorial the first week, leave this line as is. For the contour interval, this is a little different from your typical contours. You got to actually work within a interval that works within the magnitude of the numbers you are of the actual raster itself. You see that this raster is actually going from 0 to 8,000, 8,000 to 24,000, and then blah, 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 up to, say, 4 million. So if we did a contour interval of 1, this would take probably like 100 days or so just to calculate everything. So we want to work within a magnitude that makes sense for the actual raster itself. So let's say we do an interval of 5, let's do 100,000. No, let's do 20,000. I'm just testing and see what we're doing. Okay, and then I would go to environments, processing extent, same as display. Again, this is all stuff that I did in the first class. And then just click OK and see what we get. Okay, so that's not too bad. So then what we can do is, let's say some of these, we only want a specific boundary. We want to kind of really identify the mega regions of the United States. You can go into the attribute table. We can organize this by the contour interval. So I'm going to click on the contour column, click on sort ascending. And let's say we want to click, let's find, say, the 6,000 contour. If I shift select those items, let's see, maybe we want something a bit larger than that. Let's do maybe the 4,000 line. That's probably, I think the 6,000 was better. Okay, I found one that looks pretty good, which is this interval right here. So I have these contours here selected. So with those selected, I'm going to right click on this data, export data, and I'm just going to save this as mega regions. And it's only exporting the selected features, so just click OK. And so what we've created is basically a map of the biggest population regions in the United States. So these are what are known as mega regions, right? So you have the Texas Triangle here, if you know about that, San Antonio, Dallas, and Houston, the major cities in that area. You have this Midwest region of Chicago, Cleveland, Indianapolis, and St. Louis is right over here. And then you have the East Coast megalopolis, which includes, you know, Boston, New York City, those cities, Washington, D.C. So this is an interesting map because this kind of study here has been done as a way to kind of map the future growth of cities, right? These are the major population centers, and if you imagine the growth of cities in the next 100 years, this is how they're going to expand out. It's from these population centers. So people have been using this map to kind of understand like where to put train lines, or how to like organize networks and airlines, that kind of thing. So, but yeah, that's what I wanted to show with that. Okay, I'm starting the recording now. So just to quickly recap, what I did was I went to the St. Louis Police Department website and went to say the downloadable crime files here, and I downloaded a crime data set for August of 2017, last month. And so this is what it looks like when I open it up. So I'm going to format, auto-fit column width, so that way I can see all the columns and rows same way. And so what you see here is that basically each line is a line in the police department's crime data set. So it tells you what kind of crime happened, where it was located, and also an address as well. And then what we're going to use is we're going to use this last column here, which is the XY right here. So when the police department catalogs a crime, they actually have a GPS that locates the location of that crime. So this is what we can use to bring this table into ArcGIS. So it's already set up good. So we're just I just want to show you guys what it looked like, but we're going to close out of that for now. And we're going to go into Arcmap. So in Arcmap, we have the map of St. Louis. I just have the Metrolink stations just because, but let's just focus on the census tracts here. And we're going to add that CSV file. So I saved it on my desktop. So it's right here, August 2017. So that comes into Arcmap. And you see it brings in the table as it should. But what we're going to do is we're going to map the X and Y coordinate systems right here, the coordinates. So there's a way to do that. If you just right click on the table, there is this display XY data option. If you click on that, it asks for what the X field and the Y field, and it already kind of automatically shows the X coordinate and the Y coordinate as is the XY field. So this looks correct to me. You want to make sure that coordinate system is set to the Missouri East FIPS coordinate system. I think that's the one it should work with. So if you click OK, what it does is it locates every single crime event in August 2017 in St. Louis. So I heard someone said, God. And I'll tell you why you said God. It's like, oh my God, this crime happening everywhere in St. Louis. Oh my God. Everywhere you go, and it's just happening everywhere. Well, that's kind of true, and it's also kind of not true in a way, because you can do the exact same mapping for any city in the United States, and it will look probably just as similar to this. Crime happens everywhere, right? But what this doesn't do right now is it's not telling you what types of crimes are happening in which locations. And so we want to understand like, what types of crimes are happening in different parts of the city. So what we're going to do is we're going to go to this data set right here. I'm going to export this data set. So I'm going to go to Data, Export Data, All Features, the data frame. The reason I do this is just because it's whenever you're processing data, it's always good to just export it into a flat shape file. So I'm just going to call this one crime aug 2017 for August 2017. So click OK. Yes. I'm going to remove the old layer. And now let's take a look at this data set here. So let's organize it by description. So a lot of different kinds here: assault, arson, assault. So, okay, so I selected one particular data set and I exported that by itself. So now you can kind of see, and the problem with this data set is there isn't enough points of data to really create a accurate heat map, so to speak. But you can begin to understand, for instance, like the most incidents of loitering happens in the downtown area, but there are some areas around the city where you can see that happening a lot. I don't think this one's good enough for a heat map, so I'm not going to do that. Let's do instead, I believe the one with the highest number of crimes is larceny. So let's just click all the larceny options. Larceny is just basically stealing, if you guys don't know what the term means. Let's see, larceny. So we're gonna click larceny. Oh, that one's everywhere. All right, let's try, I don't want to do this, but let's try homicide, which is the worst crime of all time. But, okay. So let's go to that one, data, export data. I think one of the issues that I'm encountering right now is that there isn't enough data points to really make a good heat map, but let's just use it for now and see what happens. So let's do that. Let's go to spatial analyst, density, not density, density, kernel density, and let's use that data set here. Click on count, which I believe if you go to attribute table, the count should be 1, right? Basically all this means is that there is one value of this incident. It's the same thing as when we set the population value. We want to understand how heavy is each of these incidents. And in this case, they're all just one incident, so they're all set as 1. And again, I usually leave everything else as is to kind of see what results I get, because it's always a bit of trial and error. But I'm going to set the processing extent to be same as display by going to the environments button. Then just click OK and see what I get. So this one is a bit too generic for me. So you might want to change the search radius to be a bit more small. So let's do that one more time. Let's go to homicide, population field, and make that to be count. And let's make the search radius, let's try 50. Well, let's do 10. Let's see what we get. Environments, processing extent, same as display. Okay. All right, so to fix the issue that I was running into last time was basically we didn't have enough sample points. We needed more data in order to get a more interesting map of this particular crime data set. So I just took every month in the summer, so August, July, June, and I combined all that into one giant table. If you want to test this yourself, I did save that table as summer 2017 in the Wusto box. So what I did was I took that data set and I looked through that data set to find something that had a good amount of data to that, and so the one I chose in this case was drugs. So I took the drug data set and I used that and I plugged it into kernel density. So let's just do that real quick. Kernel density. Plug that into the first line. For population field, use count. I leave these as is. Maybe the cell size, well, that's fine. We'll make it a bit smaller so that we get a better resolution, maybe 2000. And for search radius, I'm just going to experiment here. Let's try 25. Go to processing extent, same as display. Okay. Okay. Let's see what we get. Okay. Okay, so after messing with kernel density for a few times, just messing with the search radius, we got this map here, which looks like a pretty good representation of the density of these crime points. It took me a long time to get this point because, again, it's just with the kernel density, it's really a lot of trial and error just to get to the right aesthetic that we want. So I'm just going to choose one of these color ramps for now. Let's try this blue to red one. Basically meaning that blue is where there's less crime and red is where there's more. And we're going to change the classification to be something like geometric interval. So you can kind of see that it kind of starting to look more like a proper heat map. So then what we're going to do is you look at this right now, it looks kind of pixely, right? There's actually a way to fix that within the Symbology tab. We'll just go to display, and then in this resample display, you go to the Bilinear Interpolation option. If you click on that, it smooths it all out. So this looks a lot nicer as a gradient. And so right now it's using the classified option, but if you try something like stretched, for instance, and click apply, you see this creates a more continuous looking gradient. And this is what I want for now, because I want to use this to create that hex map that I showed you guys in the previous tutorial. So I'm going to show you guys how to do that with this data set. So what I want is a drawing that looks like this black to white gradient. I'm going to see if I can change. Let's try the classification. Let's try histogram. That looks okay. Let's try. I'm just going to play around with this to see if I can get something that looks nice. Okay, that one looked pretty good. So what we're going to do is we're going to bring this into Rhino. So what we're going to do is, here's how we do that. I'm going to go to the layout view. I'm going to make this drawing here fill up the entire drawing set right here like that. Before I do anything else, I'm actually going to do this. I'm actually going to draw a bounding box because we need to scale this within Rhino so that it fits within a bounding box. So I'm going to create a bounding box. I'm going to create convert graphics to features. I'm just going to call this one bounding box. I don't know if I showed you guys this in the previous class, but this is how you create a bounding box. Is you go to the drawing tab, click on the box, and then draw a box, then use the convert graphics to feature option to create a box. Now it's a shape file. The reason why I do this is because we got to use this to trim the raster output. So create a bounding box, and then I'm going to zoom in to this feature like so. And then I'm going to export this. So go to File, Export Map. Then I'm going to export this. Since it's a raster image, you got to want to export as a raster format, so JPEG is fine. And 200 dpi is fine. Let's do that. And we'll call this one heat map drug. Save that. Okay, so then what I'm going to do is I'm going to do one more thing. I'm going to turn off the raster. I'm going to give the bounding box a black color. Then I'm going to export this as a Illustrator file. Actually, I can export it as any format. I just need to Photoshop the map to crop to that box. So I'm going to export it as, I think a JPEG will work fine. So we'll do a JPEG. I'll call this one bbox. Okay, so real quickly. So all I did was I brought this into Photoshop. Again, the only reason this box around here exists is so that I can trim the exterior and then trim this. So I go to Edit. Where is it? Edit. image trim. It's an image trim, transparent pixels, and that just gets rid of all the exterior stuff. So I'm just going to save as JPEG.
You're still recording, right?
Yes, this is recording right now. I just want to save that. So then what I'll do is I'm going to go back to Rhino. Arcmap. I'm going to export this bounding box with say these census tracks. So I'll just go to export data, export to CAD, census. I'm going so fast because I just want to end class for you guys, because I know you guys are tired. I just call this one STL B-box. You can watch this over the weekend if you want to follow along. If you remember this, to export to CAD, you always want to do same as display for output coordinates, for processing extent, same as display, and for cartography, same as display. I'll click OK. What I'm going to do is I'm going to bring this CAD file into the box folder so you can just use this for the demo. So I'll remove that. It's right here. I'm going to data, look for, I'm going to copy this to here. Okay. So then Rhino, open that data set. So you see we got it all in here, right? Okay, so we got to this point. What I'm going to do is I'm going to create a new layer. I'm going to call this one map. Set that as the current layer. And I'm going to use the picture frame tool. The picture frame tool, I believe, is in Surface Tools, and I believe it's right here. This thing called picture frame on the side. If you don't know, just type in picture frame. Yep, it's there. And we're going to use this to bring in that map we made, so that heat map. So this is why we create that bounding box, is that when you bring this map in, it matches this extent here. So you see it lines up with the GIS export that we made. This is really, that's why we did all that work to crop that image, was just so that this thing lines up with the map itself. Otherwise, you're working without a scale, which makes no sense. So I'm going to turn off everything else for now. And we're going to work only with this surface right now. So I'm going to open Grasshopper. It's right over here. And I'm going to just simply put this to the side. I'm going to move this down so we can look at this in more detail. And this is recording, so we should be good. So this is how we take this heat map and we turn it into the hexagonal looking heat map. So what we do is we bring in a surface component, right click on that, set one surface, and click on that surface. So now that surface has been set in Grasshopper. I'm going to turn off the preview for that because we don't need to look at it. What we need to do now is we need to divide this surface into a series of hexagonal cells. So the way you do that is you go into, I believe it's in vector, I believe it's in grid, and there's this thing called 2D grid with hexagonal cells. So click on that, bring that in. It's going to ask for a base plane, a size of your cells, and how many cells in XY. Let's just first drag this into P, like so. And I believe it's on there, it's just probably really small. It's probably, yeah, it's right here. It's really small in the corner. So obviously we need to make these cells way bigger than they currently are. So we'll bring in a panel right here so that I can change the number of the cell size. So we'll plug that into S. Let's try 100 to see what we get. Looks too small. Let's make it 500. Looking a little bit better. Let's make it 1,000. I just want to get it to a size that makes sense for this map. That looks okay. So I'm going to do 1,000. And then in the X and Y, we just want to make sure that these numbers fill out this map here. So again, I'm going to bring in, you can use a slider as well. I'd like to use panels just because they're a bit more secure. Let's do 100 and see what we get. So copy and paste, plug that into X and Y, so it looks okay. Let's just make it fit. So it looks like we can cut this one to 50. And we could cut this one to maybe 70. maybe 60. Looks okay. Okay, so now we have our hex that's overlaying on top of the map. Now what we want to do is we want to get a parameter. What is a parameter? A parameter is basically how does this cell map read the surface map so that it understands what, at this coordinate, so to speak, what does it mean at that level of gradient. So what we want to do is we want to take these points here and want to intersect that with this surface. So there are various tools you can use to do that. They're in the intersection option here, but we can do surface line, right? That works kind of pretty well. It gives you a parameter, which is important. So what that means is basically I'm going to take the centers of each of these cells. So let's go to this point here. If I type in point, plug that into the P, that gives you a center point for all the hexagonal cells. So we're going to use these points, and this is going to seem weird, but I'll just show you. We're going to draw a line vertically from each of those points using the line SDL component. So you plug in the points to the S, which is the starting point right here. This automatically creates a vertical line out of each of those points. If I make the line length, like say 500, you'll see that it creates a vertical line from those points. This vertical line we can intersect with the surface to get a parameter. So taking this line here, what we want to do is we want to intersect it with the surface. So that's the surface right here, right? That's the original surface we brought in. So that needs to go into the S, base surface right here. So I plug that, drag the surface into the S right there like that. And I plug the line into the L like so. And you see this has now created an intersection point at each of those lines. Now here is the important part, is this UV value. If I plug in a panel into that, you see basically what it gives you is a coordinate at each intersection point. Now, what does this mean? Well, basically all this. Now, one thing you want to do when you do anything like this is you want to use a process called reparameterizing. What does that mean? Basically, what it means is you need to take the domain of this surface, how long it is in the x direction, how long it is in the vertical direction, and I want to squeeze it into a domain between 0 and 1. And that is what reparameterizing does. If you don't understand it, that's okay. Just follow my steps. Right-click on S and click on reparameterize. And if you look at the UV values, that results, you see that the coordinates are all now between 0 and 1, whatever it is, right? This is important. I'll show you one in a second. Because what we need to do now is we need to use the image sampler tool. Whoops. Image sampler. And in here, we can bring in that raster image of that map. So I'm going to double click in here and then just choose a file path in here. So click on the dotted lines here, and we're going to find that heat map right here. Like, see, so it sort of brings in that heat map. Now you notice X domain and Y domain here, right, is going from 0 to 1 and 0 to 1. That's why we reparameterize, so that when it's looking for the coordinate, it maps it according to this domain. That's why reparameterizing is important. And then what we want to do is we want to read this map by using its brightness level, or rather how dark and how light it is. So for the channel layer here, you want to click on this color brightness option. If you do all that, just click OK. And then you can plug in the UV into this, and now it's reading at each of these points, it's reading what the color brightness is at each of those points. So we're almost done, so I'm going to turn off the preview for all that. I'm going to start to match these numbers here. You see it's a number between 0 and 1, right, which basically signifies the color brightness. And we're going to match that with the center points of these hexagonal cells. So before we do anything else, we always want to make sure that the two tables have the same exact tree. So we notice that these are grafted and these are not grafted. So we want to make sure these data trees match. This data set here is grafted. So this here also needs to be grafted in order for the trees to match. Grafted basically means that each data item is within its own tree branch or a header. You see here, each of these dark yellow headers represents a branch. Here it's dot matching. Whenever you want to cross-reference data, you always want to make sure that their data sets are matching. So I'm going to graft this tree by typing in graph, plugging in the P cells into that. And if I plug that into here, you see now that these two trees look identical, right? They have same number of branches. We can examine the tree structure by bringing a parameter viewer to make sure they match. This is data with 3,000 branches, and this should be also data with 3,000 branches. They always have to match when you're cross-referencing data. So these look like they're matching. So what we're going to do now, we're going to do something very simple, is we're going to take the numbers that resulted from this brightness, it's just a number between 0 and 1 that represent the brightest, and we're going to use this as a scale factor. So we're going to use that as a scale factor for the hex cells. So I'm actually going to graph the cells as well, because this is not just a point, it's actually a cell as well. So this is the cell up here, and this is the center point of the cell, and this is the scale factor. So type in scale, scale uniformly in all directions, this guy. It's going to ask for a geometry to scale, which is the cell right here. It's going to ask for a center point, which is this. So you see what it's doing now is it's scaling everything by a factor of 0.5, but we're going to use this number right here. So now what you see is that the map has now matched the background of this. If I hide this, you see that it creates a hexagonal heat map of this drawing right here. Now, why is this thing red? It's because we are scaling some of these by a factor of 0, which makes no sense. So what we want to do, if you don't, I mean, this works fine, the result is what it is, but what I might recommend doing is to remap these numbers. So the way you do that is you type in remap. And basically what it means is I'm going to change the domain of these numbers to fit a new domain. So right now it's between 0 and 1. Maybe it's want to make it from 0 to 1 and instead make it 0.1 to 1. I'll show you what that means in a second. So basically the first V is the value to remap, which is these numbers here. So plug that into V. Source domain is 0 to 1, which is correct. These numbers here are from 0 to 1, so we don't need to mess with that S. And then the target domain is going to be what we want these numbers to be now. So let's make this, say, 0.1 to 1. Plug into T. Then plug this result into the scale factor. You see what it does now is it took all those 0 values and just made that into a 0.1 value. Then just ramped everything else accordingly to that. And you can even make that 1, for instance, you can make that 1.2, 1.2, for instance. You can make some of the middle squares bigger and overlap with some of the other squares.
Some of the squares are on the edge.
And then when you're done, all you do is you just make a new layer and you bake that result. And voila, you got a cool looking heat map that is not just your standard, density gradient, but it actually has a little bit of interest in terms of its mapping look to it. And that's it.